Cool. So excited to be here at WalletCon. Wallets are really important because they allow us to sign things, and digital signatures are critical for the security of the applications that we're building. But when it comes to digital signatures, they usually make us kind of compromise on user experience. And so that's why I'm going to today talk about how we can use DID to improve both the security and the user experience of our applications. But before we dive into that, like why is this even a problem? Like we have wallets, they sign things that happen on chain, and that seems pretty secure, right? Well, if we look at the Web3 ecosystem today, we can notice that a lot of the data that's not on-chain data, like all of the non-financial data essentially, gets siloed into different applications. So we have a bunch of tools for DAOs where we end up doing task management, issue tracking, and like talking about proposals. All of that data is kind of siloed, especially inside of its own domain. We are starting to see some like social protocols. These are also have maybe composability in between them, but they're still kind of locked into these different things. And for reputation, it's actually a problem because we can only use financial on-chain data for building reputation systems for our community. But what if we could actually leverage all the data that we generate as we like govern our DAOs and build knowledge graphs and things like this? Yeah, so ideally, the Web3 vision, we want to be in a place like this where all of the data that we generate is actually composable and usable across these different domains. So for example, I might be contributing to a knowledge graph, and I have my avatar being my Web3 social profile. And as I'm building out knowledge in this graph, I gain reputation in some reputation system. And then eventually this knowledge that I've created is being used to make decisions inside of a DAO. All right, so we're obviously not here right now, but how do we get here? Well, doesn't signing with Ethereum kind of solve this? Because now I can use my Ethereum wallet to just like sign into the application. And the answer is kind of solves part of the problem, not fully. This clicker is a little bit double. All right, so with signing with Ethereum, we end up with something like this, where all of your interactions with your wallet are, of course, on Ethereum, but as you sign into an application, the application can pull data from Ethereum, but all the content that you generate as you're authenticated with this application ends up in the database and the backend of this application. And so while the financial data is kept in a kind of public permissionless place, all of the user-generated content is stored in these servers and being siloed. So ideally, we could have, and we can't really like use Ethereum to store all of our comments and likes and things like this. Like the security of Ethereum is requires us to have like not the throughput we can have for like say like a Twitter. So ideally, we have some other sort of network that can keep track of states that's non-financial in nature. And when we sign in, we can have data be stored on Ethereum for like the financial security type things, and all the other data be stored on some other network. So this could be a great first step. However, you'll probably notice that when you interact with Ethereum, you tend to always get a pop-up saying like, hey, do you want to make this transaction? And this is great when we're dealing with sending tokens or NFTs or something like this, where we actually want this security level of I'm doing something with like financial assets. But when you're interacting in a social network or writing a blog or making a comment, liking something, you want to always have to like accept that in your wallet. So we need something that actually, like it's not sufficient to just like have another state network where you sign everything with the wallet. But we actually want the property that we get when we sign something. We want to be able to look at this data at some point in the future and know that this like actually came from this user, and I can verify the signature of this like. So ideally, we can create a system using signing with Ethereum called session keys. And session keys allows us to delegate access to a key that lives inside of the front-end application that the user is using. And now I sign one message, and then the session key can take a bunch of actions on my behalf. So I sign in once, and then you can start making comments, upvoting things, and so on. And then the application servers end up maybe becoming thinner and thinner, but they can also read data both from Ethereum and from this general data state network. So how would this actually work? Well, to understand that, let's do a quick primer on DIDs. So DID, the concept is actually pretty simple. You have an identifier, which is basically a string. Usually it looks very random. And you can resolve this string to a DID document that contains public keys. And there's also a DID method here. And this method essentially tells you how you take the identifier and resolve the DID documents. So there are two very simple DID methods that we're going to talk about today. And they're very simple, but they're quite powerful and enable us to make this session key system. The DID key is, you can think of just as a public-private key pair, and the identifier actually encodes your public key, and you resolve this deterministically. It generates the DID document based on just the identifier. Similarly, there's another DID method called DID PKH, and you can think of this as your Ethereum account, but actually you can use DID PKH, which stands for public key hash, to represent any blockchain account. So that could be on Ethereum, it could be on Tezos or Bitcoin. You can represent any blockchain account in this way. And these are really powerful primitives to combine, because now we can have a system that can use a DID as an identifier and be compatible across multiple blockchain ecosystems. And so both PKH and DID key are generative DID methods, which is statically mapped. There are also more sophisticated DID methods that allow you to rotate the public keys in the DID document and so forth. But for our purposes, we don't actually need that, and these simple primitives can actually be quite powerful. So how do we actually use these DID methods for something meaningful? So let's talk about the session keys again. And let's imagine this scenario where you come to an application, and when you load the application generates a DID key, a public-private key pair, locally in the browser. Then it sends a sign-in with Ethereum request saying, hey, do you want to give this application and session key access to read and write these particular resources? And there's an expiry date, so for 1 week, let's say. And you as a wallet user, your Ethereum account or whatever wallet it is, have this DID PKH implicitly. And now you can choose, okay, do I actually want to give this application access to these resources? You sign this message if you agree, and send the signature back to the application. The application then takes this message and the signature, encodes that in something called Cacao. So that's short for chain agnostic object capability. And now the application can use this object capability together with its own session key to sign transactions on behalf of the user. And so in order to be able to act on behalf of the user, it creates some payload, signs it, includes the object capability, the Cacao, and sends it to some protocol. And this protocol that controls this resource, of course, needs to support this type of object capability. But if it does, the user can freely delegate access to that resource. So let's have a closer look at how we actually, this capability delegation looks like and how it works. So we've been working together with the Spruce team to extend signing with Ethereum with something called Recap. And I realize this might be a little bit small to see on this message on this screen. But essentially, this is a normal sign-in with Ethereum message. And so we have at the top, we have your Ethereum address. That's your DID PKH. We have the URI, and that's DID key. That's the session key in the browser. And then there's at the bottom, there's this random string of numbers. And that's the recap capability thing. And we can see that being decoded at the very bottom, where it says, in this case, ceramic access to read and write on this particular model. And the cool thing with recap is that it actually enforces the verification to also include in the statement of the signing with Ethereum message that I further authorize the stated URI to take the following actions and read and write to this particular model in Ceramic. And so you can, of course, use this for any type of protocol. But in my case, I'm building Ceramic, so we use this to delegate access to session keys from users' wallets in this way. Okay, so how do we actually use these capabilities? Oh, and one thing to note is you can actually encode multiple capabilities at once. So you can have like one that might be writing to Ceramic, one that might be requesting some data from a server that's access controlled, and so on. So you can like embed multiple different capabilities all at once in one sign-in message. And so how do we actually use this in Ceramic? Well, in Ceramic, the core primitive is an event stream. And an event stream is a hash-linked data structure that is synchronized between nodes in a peer-to-peer fashion. So every stream has an identifier, a stream ID. And if you spin up a Ceramic node, you can ask the network, given the stream ID, give me all of the events, and automatically verify all these events. And this event stream is controlled using a DID. When you create the first event of a stream, you specify, hey, this DID, for example, an Ethereum account, a DID PKH, controls this stream. And now I can, as a user, delegate access to update a stream to an application. And this application can now send these object capability-based signed transactions to Ethereum, to this event stream. And the Ceramic node will automatically accept that because it sees the capability delegation that was created by the user. All right, so far, so good. What about the expiry? So if you remember in the previous couple of slides, there was an expiry date, so maybe you set that to like a week. So let's say you have an application, you start writing a bunch of data with these 1 week long capabilities. That's all and good, but then I come to, I want to synchronize this data 1 year later. So I connect to the Ceramic network and start to synchronize. And then I start to synchronize all these events and I see like, oh, but this capability actually expired like a year ago. So the signature isn't really valid. This is a problem, right? Because we want to be able to verify the integrity of all the data that the user has generated. So how can we solve this? Well, the naive solution would be to like, maybe I can just trust the timestamp of the other node. But we're in a community that care really much about just trustlessness and being able to do this without having to trust anyone else, and we can verify this fully. So what we do in Ceramic is that we periodically anchor the data events into the Ethereum blockchain by including the hash of the event in a Merkle tree structure. And this allows me to, when I'm synchronizing the entire event stream, I can see like, okay, here's a time event, and I verify based on the Ethereum blockchain when the time event took place. And then I can see like, oh, it took place a year ago, so the signature is actually valid, and this object capability was used at the right point in time. Okay, so this is kind of a very low-level data structure. So how do you actually use this to build applications that give users a great user experience, and also it's not terribly complicated to use for application developers? Well, I'm pretty excited to say that yesterday we announced something called ComposeDB. The beta of ComposeDB, which is live on the Ceramic mainnet. And this is a composable, decentralized graph database where it runs on top of the Ceramic event streams and builds indexes of something called data models. And data models can be created to represent like a comment or a like or something like this, basically like any sort of data that you can imagine. And applications can freely choose which data models they want to synchronize. So now the architecture of an application like this would be something like this, where you have the wallet, it delegates access to a session key, and now each application chooses to run a Ceramic node. And so you have these 3 puzzle pieces here representing data models. One might be like a profile, another might be a blog post, another bit might be a comment, And so some of the applications only care about a subset of these data models, with one application here at the bottom has like this, okay, I'm a super application, I want to import all of the data. And they all can connect to the Ceramic network and only synchronize the data that they care about. And so you can see here how we in Ceramic leverage this session key capabilities to make a system that allows us to build more scalable and more user-friendly type of applications. But you can, of course, apply these session keys in other places as well. So the data models in ComposeDB is created using the GraphQL schema definition language. It looks something like this. So you might have application 1 creating a proposal, application 2 seeing like, I like proposals, but I also want my users to be able to comment and discuss proposals. And the cool thing is, application 2, as it's building this and importing the first data model, any proposal created in application 2 will actually also be visible in application 1. You read and write these data models using kind of standard GraphQL. To your right here is a GraphQL mutation. And key thing to note here is like when you make this mutation, as long as the user has given permission before, there's no signature pop-up in your wallet that the user needs to be prompted with. Everything can kind of happen in the background with these session keys. Right, and there's also a growing data ecosystem of Ceramic. There's actually already 2 data explorers. So one is SurfScan here, the other one is s3.xyz. And so this is the kind of interface you would go to explore like what data models exist and how are they being used, and I can just import them into my application. All right, so I hope this gave you an idea of how you can use DIDs and in particular session keys with signing with Ethereum to just like make the user experience of your application much better while still tying all the actions that the user took to an actual blockchain account.
Have you thought about how some of these data models might be kept private, or at least some of the data within them be kept private?
Yeah. So by default, data in Ceramic is public, but you can, of course, encrypt the data before you put it into Ceramic. The challenge you're going to have when you're encrypting data into a system like this is that how do you actually build indexes? Because if all of the data is encrypted, it's not easy to like index all of that data and say something meaningful about it. And I think the key challenge that we need to overcome as a community is having a way to tell the wallet like, hey, I want to encrypt or decrypt this message. And that's not something that is like currently well established in the wallet space. Most wallets mainly care about signing messages that go on chain. And so I think as a call out to like this conference, like how can we coordinate around building standards for encrypting and decrypting data natively with wallets? That would be awesome.